Okay, still example 2. Just now we have missed the calculation of power factor. So power factor D is our power factor. P is equal to F power factor is equal to P over S. If you remember our triangular power factor diagram. Okay, P, Q, and S. So the lower the imaginary power, let's say the Q, the smaller the Q, so the more S is S to represent P. And is that when we convert the cos theta here, it becomes almost 1. So it means that if the angle is lower, so the cos theta is higher. The amount of cos theta is higher. It means that the power factor is high, and the P is higher, and the real power is higher. The system is more efficient. Efficiency is increased. Okay, for half-wave rectifier, generally we have or it maintain at 0.71, but you have to prove it. You have to prove it, however, in the calculation. So power factor is equal to P over S. P anyhow is equal to I square R. And P can be I square R. It can be VI. It can be V square over R. It can be V square over R. Depends on the values or parameter that you have at that time. You can use any of the parameter. So we have calculate in terms of the average current. So what else we have? Average current obtained here. I naught. We can find the IRMS. We don't know what is the voltage drop across the load, so we can say that P is equal to I square R. We know the amount of R, and our R is known, which is 5 ohm. So P is equal to I square R. I is IRMS. So we have to find IRMS. Meanwhile, Q is equal to S is equal to VI. S. So we are comparing between the S that delivered from source versus P that received at the load. Comparing between S, the delivered power, compared to the received power, and supply and receive. Meanwhile, the Q is the losses in between. Okay, S is equal to V RMS times IRMS. VRMS. So you have to find what is VRMS, IRMS, or you can put into the calculation. So in calculation, you can say that PF is equal to P over S. So we rewrite again. The P is IRMS squared times R over VRMS times IRMS. So we cancel this RMS. So it remains as IRMS times R over VRMS. If we take a look at this IRMS in the statement earlier, so it becomes, you see here, IRMS is equal to VM over to R. VM over to R times R divided by VRMS. So we cancel the R, remains as VM divided by 2VRMS. So we have already VRMS, which is in the question 240 volt. VRMS. Okay. Vmax is our, we calculate before, which is 344. Is it? 340. 340 divided by 2 times 240. So you get 0.71. So this is your power factor. Okay, settle for example 2. Next, example 3. So now the example 3 we are using transformer. And we are using transformer. The transformer is to step up. Step up voltage or step down voltage. But the P incoming is equal to P at outgoing. The power is not being altered. It just may be that the power of the transformer, the efficiency may be not 100%, and the efficiency is not 100%, so it might have a loss. But initially we consider this one as ideal at the time being, for the time being, as ideal. So it means that P losses is equal to 0. No P losses. So P1 is equal to P2 at this time being as an assumption. Okay, it means that N1 ratio to N2 to differentiate or will determine how much V in and V out, or V at this place versus V at this place. So P1 equal to P2 means that P1 is equal to P2, V in I in is equal to V out I out. Okay. V1 dengan V2, I1 itu adalah yang sama lah. So let's say we are stepping up the voltage, means that stepping up the voltage means that output voltage is higher compared to initial input voltage. Okay. V in is lower lah. Step up the windings. It depends on the windings. So if let's say the winding of N2 is higher, so we are stepping up. Winding of N2 is lower, so we are stepping down. So that's different, or the concept of transformer. So now the question is that we need to know how much. We assume transformer and the diode is to be ideal. Supply voltage 240 volt, 50 Hz. 240 volt, 50 Hz. R we have 20 ohm. So we write it down to the schematic. How much turn ratio we need to determine, or we need to set such that the output current is 12 ampere. I average is equal to 12 ampere. So N1 and 2 is how much? Okay, that's what we need to find. Then what is the average current on the primary winding? So I1 is how much then? So we will draw again in the next part, which is first thing you have to do is that you have to rephrase again the VT here. Vs is equal to Vm sine omega t. So Vm we have 240 set to sine 2 pi f times t. So 340 sine 100 pi t. Okay, this is your rephrase statement for your voltage. So I0 you have to set at 12 ampere. How much your turn ratio? Okay, you can see here when you rewrite, you can stick it like this, or you can solve such that it becomes 240 like this. Okay, then the I out you already determined, which is 12 ampere. So you find for I average equation per Ohm's law. I0 is equal to V0 over R. So this is on the secondary side, N2 side here. Means that V0 at secondary divided by R. So we know that V0 here is equal to V max over pi. So you replace V max over pi, and you shuffle the statement over there because we need to find the Vm. So Vm is equal to V max here. V max here is equal to pi times I naught, which is, we already know the value, which is 12 ampere times 20 ohm. 20 ohm, which is totally the voltage that we expect to be generated at secondary voltage winding is 255 volt. So this is our secondary side voltage. Secondary side voltage, this one, the peak, the air peak and peak. Sorry. Now we are considering the peak. This is average, but this one is Vm peak. So the peak value here, 754 volt. So what about the turn ratio? What about the turn ratio? From 200 volt to B754 volt. 200 volt to B754 volt. How much is the turn ratio? So we can see here, N1 divided by N2 is equal to Vm1 divided by Vm2. Because the higher the turn ratio, the higher the voltage will be generated. So N2 should be higher compared to N1. We are stepping up. So Vm2 should be higher compared to Vm1. So means that we are, if 1 over 2, so the number should be lower than 0. So we have here 240 volt times 2 divided by the voltage we generate at secondary side. So the turn ratio is 0.45. What about the average current on the primary winding? So as we stated before, P1 is equal to P2. Vi1 is equal to V2I2. Okay. And also, so we have here, if you take V1 over V2, so it becomes I2 over I1. Okay, so you change the place here. V1 over V2 is equal to I2 over I1. So you get here N1 over N2 is equal to Vm1 divided by Vm2 equal to I2 divided by I1. So you will get this number, or the value of current at I1, I primary here, is equal to 26.67 ampere. Okay. If you cannot remember the equation, just remember this one. You derive from the P. P1 and P2 is the same. So V1 and I1 is equal to V2I2. So you can cross the place you can find the equation. Because we already know the current here, which is 12 ampere, and 2 I2 already known. So only the unknown is our I1 here. So you get I1 with the value of 26.67 ampere.